Dear students, welcome to our class. Today we are going to discuss the topic of diffraction. What is diffraction? So before going to the diffraction, we can see small introduction about diffraction. See, the phenomena of diffraction was first discovered by Grimaldi in 1665. Who is that? Grimaldi. The phenomena of diffraction first discovered by Grimaldi in 1665. Bending of light around the edge of an obstacle is called diffraction. Generally, the diffraction definition it will be in layman language, that is bending of light around the edges of an obstacle is called diffraction. If we can observe the diagram here, the diffraction pattern, here this diffraction, the image, it can explain the sound waves. Here it is explains about the light waves. Here it is sound waves and here it is light waves of a diffraction. In sound waves we can observe the small object around the similar size of and to their wavelength. See, one girl is coming to her direction and another girl, she came from another direction, and their wavelength, the similar wavelength of around the objects. The wall has been similar size to the sound wavelengths. The effect is called diffraction. And here it is, the light has a very small wavelength. Light has very small wavelength, so only very small objects or gaps can affect its direction. Okay, the wall blocks the light and a person can't see around the corners. In light waves, you can observe they can't see the corners, but in sound waves they can similar wavelength in the sound waves. See, a small video, the next slide. See, this is the architecture of Roman or whatever in Europe countries. It is one of the construction based on diffraction. See, here the sunlight, we have natural light source, that is sun. The sun is appears into the hall with bending of light. Here we can observe here the bending of light, it is through the diffraction phenomena. Coming to next slide. See, here it is diffraction of light. Here the diffraction of light, it refers to the various phenomena that occurs when a wave encounters an obstacle or slit. It is defined as bending of light around the corners of an obstacle or aperture into the region of geometrical shadow of obstacles. Here we can observe the diagram here. It will be in waveform. Here it is the waveform. Here it is the pattern of circular formation. See, like we already heard about the Newton rings, in such a way that if you can applicable to the Newton rings, so see, these like in Newton rings, the pattern of circle in shape. The diffraction pattern of red laser beam made on a plate after passing through the small circular aperture in another plate. See, here this is the phenomena explained by the Young's modulus, Thomas Young's. He is the one of the famous scientist in our physics, that is Thomas Young's. He sketched or explained the two-slit diffraction which he presented to the Royal Society in 1803. After that, again after Young's modulus, one more famous scientist is Huygens principle. Huygens or Huygens, he is the one of the famous scientists. He explained the pattern of diffraction. The pattern of diffraction. See, Huygens postulated a model for light waves similar to water waves. On the basis of model, he proposed a hypothesis. What is hypothesis? It will be maybe or may not be. Hypothesis for geometrically constructing the position of wavefront. Then, postulate 1. Each point on a wavefront acts as source of new disturbances called secondary wavelength. See, if you can observe the diagram here, the wavefronts, these are the wavefronts, and here it is the slits. The slits, that is two slits, that is two barriers or two obstacles. Through the obstacles, they form a wavefronts or wavelets. And coming to second postulate, the surface touching these secondary wavelengths tangentially in forward direction at any instant gives a new wavefront called secondary wavefront at the instant. Okay. In general, diffraction occurs when wave passes through the openings. Here it is openings around the obstacles or by sharp edge Next one. See, the construction of secondary wavefronts. In previous diagram, we had seen that is how the wavefronts has happened, and here if you see this diagram, the resultant of the single slit can't be explained by the geometrical optics. The geometrical optics would say that light rays traveling in straight lines should cast a sharp image of the slit on the screen. See, here it is without diffraction and here it is with diffraction. Without diffraction, with diffraction. If we can observe the without diffraction diagram, see, if you see here it is the slit and it is form a without diffraction and it is passes through the only in single ray. In without with direction, it form as a the wavefronts it's appear geometrical region. Here it is the geometrical region. Here it is geometrical region with diffraction. See, we can observe here the construction of secondary wavefronts. So this is the one wave. Here it is, S will be the propagation of light or source, whatever it is. Then the first wavelength, then it is A, B, A, F, that is, and the A from A to B, it produces secondary wavelets and second form of wavelengths will appears and forms. Then it is according to Stokes law, one of the famous law, it is the intensity of spherical wavelets varies as 1 plus cos theta by 2. 1 plus cos theta by 2, and here it is the theta will be angle between direction of propagation of wavelet and the normal at the point. For backward direction, from the backward direction, theta will be 180 degrees, therefore intensity will be 0. What is intensity will be? Why it is intensity will be 0? The background directions. From background directions, theta equal to 180 degrees. So therefore the intensity will be 0. Intensity 0. Next, the difference between interference and diffraction. Generally in interference, we can say what is interference? The superposition of light and it is passes or travel to the same wavelength and same frequency, right? Coming to the difference between interference and diffraction fringes. Here it is, first one will be interference fringes and diffraction fringes. All fringes are for equal width. All fringes are equal width, that is in diffraction the width of the central maxima is twice that of other fringes, and all bright fringes are equal intensity in interference fringes. Here in diffraction fringes, center fringe is the maximum intensity and the secondary maxima are decreasing intensity. Secondary maxima will be decreasing intensity. We will discuss about the what is secondary maxima and minima in further slides. Okay. The maxima occurs at the path difference between two waves of n lambda, and the minima at path difference will be, that is n plus 1 by 2 into lambda. Okay. Next, coming to diffraction fringes, the minima occurs at path difference of n lambda and the maxima at the path difference will be n plus 1 by 2 into lambda between the waveforms of the ends of the slit. And coming to interference fringes, it is the resultant of interference of two different wavefronts of two coherent sources. Okay. Interference phenomena. Generally, the definition of interference phenomena, two coherent lines with superimposition of with travels through the same wavelength, same frequency, that is known as interference. What is coherent? So the waves, two or more waves having same frequency, same wavelength, that is known as coherent source. Coming to diffraction fringes, it is the result of interference of waves from the different parts of the same wavefront. And interference fringes, minima has 0 intensity, and here is diffraction fringes, minima are never perfectly dark. Here it is, minima are never perfectly dark, it is geometrical shadow region. Okay, there is no perfectly dark in diffraction, but the shadow, which shadow? Geometrical shadow region. And coming to the types of diffraction, here we have two different types of diffractions and important diffractions. One is Fresnel diffraction and second one is Fraunhofer diffraction. So what is the Fresnel diffraction occurs? Fresnel diffraction occurs when the source and the screen are at a finite distance. What one it is? Fresnel diffraction occurs when the source and the screen are at finite distance. See, it is finite distance from the diffraction aperture such that the incident and diffracted wavefronts are spherical or cylindrical. Spherical or cylindrical. If you observe the diagram here, it is finite distances, and the wavefronts will be either spherical or cylindrical. And coming to Fraunhofer diffraction, it will be when the source and the screen are at the infinitely large distance. What is that? Infinitely large distance from the diffraction aperture, such that incident and diffracted wavefronts are the plane. Here we can see the in diagram it is parallel rays, and the distance between from slit to screen, it is infinite distance, and here Fraunhofer, it is finite distance, So the relation between Fresnel diffraction to Fraunhofer diffraction by a single slit. Okay, next one. The phenomena of diffraction. Diffraction of a light is a phenomena of bending of light waves around the corners of an obstacle or an aperture placed in the path and either spreading into the region of the geometrical shadow. Next, diffraction becomes significant when the dimensions of aperture or obstacles are comparable to the wavelength of the light. It occurs due to manual interference of the secondary wavelets starting from portions of the primary wavefront which are allowed to pass through the aperture. So this is the perfect definition for the phenomena of diffraction. That is, diffraction of light is a phenomena of bending of light waves around the corners of an obstacle or an aperture placed in the path and either spreading into the region of geometrical shadow. I hope you are all following the slides. So coming to the difference between two types of diffractions, that is Fresnel diffraction and Fraunhofer diffraction. Here coming to Fresnel diffraction, that is cylindrical wavefronts. In Fraunhofer diffraction, it is planar wavefronts. Fresnel diffraction, the screw from the source to screen, it is finite distance. From source to screen, it will be infinite distance in Fraunhofer. Next, it is move away that directly corresponds with the shift in the object. It is fixed position. In Fraunhofer, it is shifted in position. Then coming to Fresnel diffraction. Fresnel diffraction is a pattern of flat surfaces. See, the surface will be flat here from source, and here it is the slit, and it is passes through the slit or barrier or obstacle from source to the screen, and change as we propagate them further downstream of the source of scattering. In Fraunhofer diffraction, the Fraunhofer diffraction patterns on the spherical in surface, and shape and intensity of Fraunhofer diffraction pattern, it is constant. So this is the major difference between Fresnel diffraction and Fraunhofer diffraction. I hope you all get the point. So we can here we studied or discussed about what is diffraction phenomena and what is the difference between interference and diffraction and types of diffraction and the different types of diffraction with difference, that is Fresnel diffraction and Fraunhofer diffraction. Dear students, we can discuss Fraunhofer diffraction in next class. Generally, here we are using lens in Fraunhofer diffraction, and in Fresnel diffraction there is no need to use lens. Here we can observe the diagram. Here it is the slits. Here it is the slit, and here it is the two lenses. Here it is from source to lens 1 L1 and lens to L2. So in Fraunhofer diffraction we are using lens. In Fresnel diffraction we don't use lens. This is the major difference of Fresnel and Fraunhofer diffraction. In next class we can discuss about the Fraunhofer diffraction due to single slit. Thank you.